Now I want to show how to solve part A using the concepts of work energy theorems. But before I begin, I want to quickly recap on how we solved this question using just this work equation. Now there are three elements of the work equation. You have your force, you have your displacement, and you need an angle. Now, we identified that the force was the applied force, and this was because we wanted to know the work performed by the mechanic, and the force the mechanic exerts is the applied force right here. And the displacement, or the distance, was 2 meters, and it was 2 meters upwards, so you got a positive 2 meters. And the angle, now remember, what I did here was I rotated the axes so that it looked like this. Now the applied force is on the side here, and right over here we had our displacement of 2 meters. And because the displacement vector is going to the right as well as the applied force is also going towards the right. If we connect these for a moment, the angle between these two is 0 degrees. Then the next problem that happened was we weren't given what the force was. We had to figure out what the applied force was. And in order to do that, we used Newton's second law. And we summed up the forces acting in the y direction and set that equal to the mass times the acceleration in the y direction. And because there was no acceleration due to a constant speed, because it was given that it was at a constant speed, we could cancel these terms out and reduce them to 0. And when we summed up all the forces, we proved that the applied force was equal to our force of gravity, which is also equal to mg. Now that's one way of solving it. Let's use another concept called the work energy theorems. There are 3. We have our net work, and that is equal to the change in kinetic energy. Our second work energy theorem is work done by our non-conservative forces, and that is equal to delta E. And lastly, we have the work done by conservative forces, and that is minus delta potential energy. So the change in potential energy. Now, the one that I prefer to use in this scenario is the second one right here, the work done by the non-conservative forces. So I'm going to erase this for a moment and write it off to the side. So the work of the non-conservative forces is equal to our change in energy. The change in energy. And I'll explain what that means in a minute. So again, what I like to do is I like to draw my diagram. Right here is a good representation of what is going on in the system. I've drawn my free body diagram where I label the forces, and I threw in some extra information right here telling me the displacement. Now, we have to identify what forces are conservative and what forces in the system are non-conservative. So I will represent that with the letter C for conservative forces and an NC for non-conservative forces. Hopefully that is not too confusing. Now, the conservative forces on almost any system, two basic ones are the force of gravity and the force that is created by a spring, so the spring force. So in this situation, we only have gravity as our only non-conservative force. So I like to write that down. But what about our non-conservative forces? Well, anything that is not a conservative force, it's everything else. Non-conservative forces can be the applied force, a normal force, frictional forces, and so forth. Anything that is not a conservative force. So in our system here, the applied force falls under the category of non-conservative. So now that we have established what our conservative and non-conservative forces are, we ask ourselves, are the non-conservative forces doing any work on the system? In this situation, the applied force is doing work on the system. And that is because if we momentarily think about work done by the applied force, we have the applied force and multiplied by the displacement of 2 meters times the cosine of 0. We know that the answer to this is going to be some number greater than 0. And if that's the situation here, we know that there's going to be work done by this non-conservative force. But at the moment, we have no idea what it is. So what we're going to do is utilize this work energy theorem equation right here. Now, delta E is short for mechanical energy, and delta E is our change in potential energy plus the change in our kinetic energy. And as a reminder, potential energy in this situation is the potential energy of gravity, so gravitational potential energy. And the formula for that is mass times gravity times the height. And kinetic energy is 1/2 mv squared. So let's start plugging in the values for this. So we said the work of the applied force is equal to our delta E value, which is equal to our change in potential energy, gravitational potential energy, plus our change of kinetic energy. Now let's look at the statement for a brief moment. It said a constant speed of 3 meters per second. This means that the initial speed was 3 meters per second, and the final speed was 3 meters per second. So did the kinetic energy change at all? No, the kinetic energy did not change. The kinetic energy differential, or the change in kinetic energy, is 0. And I'll write it out for a moment so that we can better see it. So 1/2 mv initial squared I should be doing final minus initial. final squared minus 1/2 mv initial squared. Now, again, to recap real quickly, I'm writing this out to show how the change of kinetic energy is 0. Because the velocities do not change and the mass is the same, ultimately, when we subtract numbers that are of equal value, we get an answer of 0. So we'll get some number here minus the same value, and that gives us 0. And this is all because the velocities did not change. So what I'll do here is put a 0 mark right there. Now what about the change in potential energy? Let's focus on this right here. Now the change in potential energy, so we have mgh final minus mgh initial. So the initial height was 0, and the final height was 2 meters. So if we write this all out, so we had 140 times 10, because gravity is 10 meters per second squared, approximately. You could use the value 9.8, but we're just going to round it off to 10 here. And the height here, our final height, was 2 meters. Minus 140 for the mass, 10 for gravity, but the initial height was 0. Though it wasn't given, the engine was lifted off of the ground, and if we define the ground as our 0 height, we can say the initial height was 0. So again, just to recap real briefly, because we lifted it off the ground, and on ground level, we consider that to be a height of 0 meters or 0 inches or what have you. So this expression right here becomes 0. So all we're really worried about in this situation is this portion right here. So we have 140 times 10 times 2. And this will give us 2,800 joules, because the unit for work is in joules. And as you can see, this produces the same answer that we got by using just the regular work equation along with a little bit of Newton's second law. So I want to briefly go over this process one more time. First, we drew our free body diagram of the system, which I have right here. Next, I labeled my forces into conservative forces and non-conservative forces. And then afterwards, I concentrated my attention on the non-conservative forces. And the reason for doing this is because I wanted to utilize this work energy theorem. There are 3, and I decided to go with this one because the work done by the non-conservative forces corresponds to what this question is asking, because the work performed by the mechanic is our applied force. Then afterwards, I wrote out the expression, the work done by the applied force. Actually, let me back that up for a minute. After I identified that what the non-conservative forces were, I needed to ask myself if these forces do any work. And the way I thought about that was, I have to very quickly think of this equation right here. Just the regular work equation. And if you get some value that is greater than 0, or it could be less than 0, you could have a negative work. It is possible. If you get some value that is not 0, that means work is being done on the system. After I identified that, I was able to utilize this work energy theorem equation right here. And then I established that delta E is the change in mechanical energy, which is the change of your potential energy plus the change in your kinetic energy. And as a little side note, this is not always what the change of energy will be. This just involves any type of energy in the system. In the system, we were dealing with gravitational potential energy and kinetic energy. Sometimes you might have heat involved. Sometimes you might have spring potential energy. And what you do here is you add up all those delta, or the change in all those energies to get your value. Then afterwards, I realized that the change in kinetic energy was 0 because we were given that the mechanic is lifting this engine at a constant speed of 3 meters per second. Then we had to look more closely into the values for our potential energy, and we wrote them out. And because we know that a delta, or a change in anything, is your final minus your initial value, we wrote out our MGH final minus our MGH initial. And we realize that the initial value goes to 0 as well, because the mechanic lifted the engine at the ground level, and we defined the ground level as a height of 0 meters. So then all we did was focus our attention on our MGH final, and we knew that the final height was 2 meters, and we had the rest of our values here. We already know what the mass was because it was given up here, and we knew what gravity was. We either used the value of 9.8 meters per second squared or 10 meters per second squared.